Okay, it's now been recorded. Okay. Perfect. Nice. Okay. So the topic of today is basically, again, so we're going to talk about sampling, which is what we've done in the last couple of lectures, but also more generally, like the more general form of sampling related to what's called global dynamics, where what we've done so far is try to sample objects from like a set of allowed objects, but then it was uniform of these objects, and now we can say, what if we want to sample something from a distribution of objects, so it's not just 0, 1, just some other distribution. And then also we'll see this notion of a spectral independence, which is a recently introduced notion over the last couple of years, that in some cases help to really analyze these dynamics in a much better way, much more streamlined way, by a connection to HDX. But actually, before I do any of that, I just want to spend maybe 5 minutes to just go over the basics of Markov chains, because we're going to see them come up today a lot. I mean, we've seen Markov chains several times in this class, but we never actually spend the time to formally define them. So it's we just formally define them, and so that we can. Also, if you read papers that people that mention them all the time, you should at least know the basics. So Markov chains. So we have some ground sets. From a graph, possible objects that you might care about. I don't know, maybe clicks in a graph, maybe matchings, maybe whatever, colorings of a graph. And we have a set of random variables. So a Markov chain is the sequence of random variables. No, Z1, Z2, Z3, and so on, which are dependent, but crucially, each Zi depends, or let's say, the distribution of Zi depends only on the last step. So somehow, if you know what happened in the last step, then there's some randomness involved in determining the next element in the sequence, but that's it. You don't need to know anything before the last element to determine that. So formally, what we could write is that, let pi t be the distribution of zt, then what we mean by that is that when pi t is determined by some matrix a t pi t minus 1. So at is the transition probability. I think here we call it at minus 1, the notes. So at minus 1, let's call this maybe VW, is basically the transition probability, what the probability that zt equals v conditioned on zt minus 1 equals w. And basically, by multiplying with this matrix, we get the probability for the next step. And then we've seen already an example of that. So, for example, what's an example we saw? So we saw the example of a random walk on a graph. G V, where omega was V, that is the vertices, and all these matrices are always the same, just the normalized adjacency matrix of the graph. Right, so this is an example we saw in the first few lectures. And one of the main, basically the main change we allow for general Markov chains is where the transition could change with time. It could depend on the time step. So in general, we can say that, so if AT is some A for all T, then the Markov chain is called homogeneous. So a homogeneous Markov chain, the Markov chain with the transition probability stays the same all the time, like the one we saw in a random walk on a graph. And otherwise, we call it inhomogeneous. But luckily for everything we need, we just care about homogeneous Markov chains. So basically, and you can actually show, we have this as an exercise in the notes, that a homogeneous Markov chain is actually equivalent to a random walk on a graph with weights, with appropriate weights. So that's actually an exercise in the notes. You can just verify these two notions are in fact the same. So every weighted graph, the random walk on the nodes is a homogeneous Markov chain, but also every homogeneous Markov chain, you can create a graph on the set of possible objects with weights such that you exactly get the corresponding probabilities. Okay, so this is basically what I want to say about Markov chains. I just want to make one more thing. So if you remember, we saw when we talked about random walks on graphs that if we knew something about the second eigenvalue, if we knew something about the expansion of the graph, then we can control, how fast it mixes. But we only analyze this for regular graphs, for which the stationary distribution is a uniform distribution. So I just want to state as fact that this thing generalizes to non-homogeneous, so to non-constant degree, non-regular graph theory. So here's a fact. So let G be a connected graph, connected, let's say, weighted graph to have weights on it, graph on weights on edges. Let pi be the stationary distribution. So just reminded me that pi equals AG pi, right? So it's a distribution of nodes that if I take a single step, I get the same distribution again. So it's what this random walk converges to. The mixing time of the walk is the following. So it's going to be order a few things. So we're going to have here, I'll write it and I'll explain. And so it's also going to be a lambda spectral expander. Lambda expander. So we have an expander. We're doing a random walk on an expander. And what we saw before, just to remind you, so before, what we saw that if G is regular, then pi is just uniform, right? The uniform distribution is a stationary distribution for walks on any regular graph. And in that case, the bound we saw was a very similar bound. But now what happened? Now we're replacing n with this pi mean. So what does pi mean? Pi mean is just the smallest probability of the transition of the stationary distribution. So pi mean is just going to be the minimum of all v and v. Pi v. So basically, what happens before the boundary was like log n over epsilon. Think of lambda as a constant for now. It was log n over epsilon, and now it's been replaced with log of, actually this is with inverse. Log of 1 over the smallest probability over epsilon. So if it's uniform over n nodes, all the probabilities are 1 over n. So pi mean inverse is exactly n. So we recover the previous bound, but actually exactly the same proof would give you this bound. So if we have a non-regular graph with some maybe weird stationary distribution, and you want to converge to it, then you need to take into account the smallest probability in this out of them. So this is just going to be a fact that will be used for us. So this is what I want to tell you about Markov chains before I go back to sampling and Larva dynamics. Any questions so far? Okay. So now let's see how we can sort of define a general sampling problem. So let's call this a general sampling problem. So we're going to have some set of elements we're going to call S. And our domain omega is going to be 0, 1 to the S. And we're going to have a distribution. So we're going to have a distribution mu over m omega. And our goal would be to approximately sample from mu. Okay, so this seems very generic. So let's see some examples. So here's one example. 2 examples. So maybe here's one example. I could take maybe G to be a graph, S to be the nodes, and mu to be uniform over k clicks. Right, so I can imagine a k click as being 0, 1, and every node is a set 1 if it's in the click, 0 if it's outside the click. So basically, omega is going to have vectors of Hamming weight k that correspond to a click in a graph, and I want to sample from this distribution. So that's the same as sampling from a random k click. I could also take maybe the same thing, G to be some graph, S to be the edges, and mu to be uniform over matchings, or spanning trees, or whatever else you care about, right? So in general, what we're saying here, they're the base elements, and each one is going to be inside or outside my solution. So it's just a little bit 0, 1. And we're trying to sample, and you see, all of the previous examples we've seen, mu was basically uniform over some set of allowed objects. But more generally, this is usually called the hardcore model, either inside or outside. The other option that people care about a lot is what happens, if mu is not, uniform. But let's say maybe S will be, maybe mu is going to be over all sets of size k, where we're going to give a higher probability for k click as of low probability if you're missing some edges. So you can sort of start to play with the things, and there are many examples like that studied in CS, in statistical physics, and in general, such a system in physics is called a 2-spin system, Y2. Well, 2 corresponds to the fact that we have 2 options. So you can think about coloring each element with 0 or 1. But similarly, you could define like a 3-spin system where it could be 0, 1, 2, or a Q-spin system, or no. You generalize very easily. So to be concrete here, I'll just talk about 2-spin systems but everything generalizes in sort of the obvious way to more than 2 options for each element, right? Like if I want to study 3 colorings of a graph, then every node is going to get one of 3 colors. That's a 3-spin system. Okay, so that's going to be the type of questions that we'll try to study. And so we see some examples. And what I want to show you is that there's this very natural MC algorithm to solve this problem, which is called the Glauber dynamics. So here's the definition. So the Glauber dynamics is a Markov chain defined as follows. So let maybe ZT minus 1 be some element, and I want to sample the next element, ZT, right, in omega. Again, omega is like 0, 1 to the S, just reminding you. So we sample it as follows. So given some possible solution, how do we solve the next solution? We're basically going to choose a random coordinates uniformly from S. All the rest keeps the same, and just this one change in a way that's according to mu. So let me define that. So I'll define this as follows. So step 1, so we're going to choose uniformly some element I in S, and we're going to set ZT at coordinate J for all J not I to be the same as ZT minus 1 J. So I think of every ZT as a vector of length over S elements. I choose one of the elements randomly, uniformly. That's the one that I might change. All the rest I fix to be at the one step before. And now I just want to change this one last element. So how do I do it? So now step 2. So we have 2 solutions left, right? We have 2 solutions left, 2 options, let's call it. We have 2 options left for ZT corresponding to setting ZTI equals 0 or ZTI equals 1. Right, here are the 2 options I have left. Only 2 options. Let's call them for simplicity sigma 0 and sigma 1. So sigma 0 and sigma 1 are the 2 options for ZT, which again are the same as ZT minus 1. Sigma 0, I set the ith equal to 0. Sigma 1, I set the ith equal to 1. So I want to choose one of them with some probability, and the probability I'm going to choose ZT to be sigma. Let's call this maybe B. So B is 0, 1 is going to be mu of sigma 0, so mu of sigma B divided by mu of sigma 0 plus mu of sigma 1. So I choose one of them, sigma 0, sigma 1, with probabilities corresponding to the probability mu gives them. Okay. So if mu sigma 0 is sort of higher, I'm going to choose with a higher probability. And basically, here's the fact. Actually, going to see a proof of it soon. So if mu in some sense, let's call this connected. We'll define this more formally in a bit. So this converges to mu. And basically connected here just means that for every 2 elements in the support, I can move from one to the other by steps, by only change one element at a time, and none of them have 0 probability. Okay, so again, if you think about the support of mu, all the elements where I can get with some non-zero probability, I need to do it for any one point, any other point there, but just this local change of changing one coordinate at a time. Okay, and this is the basic fact of the Markov chains. And again, the main question here is going to be how fast. Now, it's nice to know that in the limit of infinite time we converge, but no, in practice we want this to converge fast. So the question is, how can we analyze such a random walk, and what properties of mu would guarantee that this converges fast? So that's like the general question in the study of global dynamics, which is an area that's been studied in physics probably at least, like, 50, 60 years, maybe even more. So it started for people in statistical physics, studied this, and then moved to CS, but sort of it's still been studied a lot in these two communities. Okay, so any questions so far about the definition of a global dynamics? Okay, so now the next step, I want to show you how to connect these two HDX. So the next step, I want to take global dynamics. And connect them to high dimensional expanders. Okay, which is why we sort of teach you that. So the idea is going to be very simple to what we've done so far. So you can define a complex that exactly captures the allowed set of objects that you can take. So let's do that. So for simplicity, I'm gonna assume from now that S is just always going to be a set of coordinates, 1 up to n, just so that I can identify elements of omega as 0, 1 to the n. I mean, S is just some names of all objects, so just call it 1 to 3 up to n for simplicity. So we're going to mu is some distribution over 0, 1 to the n. And I want to define it by a complex. So we're going to define x. So we're going to let x be an n-dimensional. Sorry, before that. Okay, let me denote V is going to be the vertex of the complex to be all the options of taking an element and saying it's either 0 or 1. So it's going to be all of this provided that IB, IN being 0, 1. So elements of V corresponds to given a color or a label to an element between 1 and n, an element in S. And then X is going to be an n-dimensional simplicial complex where the base elements are V and Xn is going to correspond to labelings of all the possible elements. So Xn is going to look like all the things in the form 1, B1, 2, B2, and Bn. Well, B1 up to Bn are in 0, 1. So again, how do I want to think about this? So you should think about, my element, top phase is what's called the full coloring. I take all the n elements, and to each one I decide it's colored either 0 or 1. So I'm going to think of what Xn as full colorings of all elements. And then we can think about intermediate level phases as partial colorings. So elements in Xk corresponds to partial coloring of K elements. Okay. So this is the complex, and then you want to sort of also somehow endow a distribution of this complex, and that's going to come from the distribution mu. So I'm going to define pi n to be a distribution over the top level xn, which is exactly mu. So pi n of the face 1 b1 2 b2 and bn is going to be exactly just mu of b1 up to bn. Okay, so I mean, everything we've done here so far is, I mean, it's just identification. It said instead of looking on coloring of all the n elements, we're going to think about this complex with n levels, where the top level is coloring of all the elements. Level n-1 is coloring of n-1 elements, and one of them is uncolored. And so in general, level k has k elements colored, even value 0, 1, rest are uncolored. And you know, at the top level distribution is exactly mu. And now I want to make the following claim. That the Glauber dynamics is exactly the same as the lower walk on X. So now so we've seen already a couple of examples of that, but now let me try to explain why. So what is the lower walk? Again, think about the cases we've seen in the past. Where mu is just uniform over some set of allowed elements. So some colorids are allowed. So what was the lower walk? So we start from a full coloring. Like maybe I want to do k clicks, so the k elements are 1, the rest are 0. I choose one of these elements. I sort of, randomly change it. I sort of remove its label, and then I want to edit it later. And so that the probabilities are consistent in mu. And actually, you can verify that. Let's say if I do it for k clicks, well, if I chose a 1, now I have k minus 1 ones, n minus k 0 is one element uncolored. And then I can decide if I want to have this element to be colored or uncolored. Actually, this is not quite, sorry, I take this back. This will not give us exactly the k clicks setup, because k clicks we want to move from one k click to another k click. But this will give us other things. This will give us, for example, the random walk of like 3 colorings of a graph. Like if I give you a coloring of a graph, and you want to move from one 3 coloring to another 3 coloring, so this is like a 3-spin system. So you take one element that's colored, you uncolor it, and then you recolor it with one of the 3 colors proportional to the probabilities that you want from mu. And if mu happens to be uniform over all legal colorings, then you just choose one of the legal colors for this node randomly. The reason this doesn't quite capture walks on k clicks is because you want to move from one k click to another k click. So you basically want to remove a 1 and remove a 0 and replace this 0 with a 1. So you actually need to make 2 steps. Like you need to go, you basically need to uncolor a 1, uncolor a 0, and then recolor both of them. So actually this k click walk would just correspond to a lower walk going from level n to n minus 2 and then left to n. But anyway, you can capture many interesting MC algorithms by just studying walks on such complexes. And in particular, Glauber dynamics give you just the simplest lower walk from n to n minus 1 to n. And the question again is, how do we? So again, we know from like general techniques we've seen that the lower walk always converges to pi n, right? We know again for the same fact as before. Let's say that if sort of if x is, again, let's call this connected, then the lower walk converges to pi n, and again the question is going to be how fast. And then connected here is again meaning the same thing. They can move from any coloring to any other coloring by just making local changes one element at a time, such that they all have positive probability under mu. Okay, so this sort of shows you that understanding the mixing time of Glauber dynamics is completely equivalent to analyzing the lower walk of the corresponding simplicial complex. Okay, so now is going to be another good time to stop and see if you have any questions. So now comes basically the topic of this lecture, which is a technique used to prove this dynamics or the slow walk mixes fast. And this technique is called spectral independence. So this technique originally was by ALO. ALO stands for Anari, Liu, and Oves Garan. But since that people have sort of refined it and extended it to like more and more objects. So now it became like no, it's only a couple of years, but it became sort of like a major technique used to prove mixing of global dynamics, of what's called spin systems. So I'll define it in a way that's not quite the same as it was defined in the original paper, but in one of the follow-up papers that is actually more natural in hindsight to analyze. So this requires to define something called the correlation matrix. Let me define something that's called the correlation matrix. So again, let mu be a distribution over 0, 1 to the n. So the correlation matrix of mu is a 2n by 2n matrix. And the rows and the columns are labeled by an element and whether it's colored 0 or 1. So it's rows and the columns are labeled by basically an element and whether it's 0 or 1. And its elements are denoted by psi. So its row is going to be pair IA, and the column is going to be JB. So here I and J are in N, and A and B are just the colors 0, 1. So I comma A is an index of a row, and J comma B the index of the column. And it's basically going to be the correlation between ZI, a sample Z from U, that ZI is A and ZJ is B. Just asking about the correlation between pairs of colors of elements. So it's going to be the probability that I sample Z from U of the J's element being B, condition on the ith element being A, minus the probability that the Jth element is B. So this is it. So we're saying, well, what's the correlation between element I getting the color A and element J getting the color B? Well, we're just going to sample Z from my distribution mu and ask, compare the distribution that Zj is B, condition on Zi is A, to just an unconditional probability, again, under mu, that Zj is B. So for example, if the coordinates are independent, if mu is a product distribution, this is going to be 0, right? Because the product that J is B condition on Zi is A is equal to the whole Zj is B, right? So by the way, there's just one more tweak here. So this is here, of course, we always want to compare two different coordinates. So this is only if I is different from J. So I still need to define this matrix, what happens if I equals J. And then we just define to be 0. And if I equals J, then we're just going to set IA, IB to be 0. So we never look at the correlation between an element and itself, right? This doesn't make sense. So just syntactically make it 0. Okay? So this is a definition of the correlation matrix. And just let me make a simple claim here. That if mu is a product distribution, then this matrix is just 0, right? Because there's no correlation between the pairs. So to some extent, what this matrix is trying to capture is how close to producty is your distribution. And we're going to measure it in some sense. We haven't defined it how we're going to measure it, but we're going to measure it in a spectral sense. To see actually in natural, maybe in hindsight. But is a definition of the correlation matrix clear? Because that's going to be a crucial definition today. So I wanted to make sure that you all understand this definition because we're going to use it a lot. So I need to really make sure that you all understand this definition. So maybe take like 30 seconds, stare at it, make sure that it is clear to you. And if not, then ask now. Okay. So this is just a pairwise correlation matrix. We will also need to say, not just this is what's called the global correlation, but we will also care about what happens, if I already fix a few coordinates. Like what if I fix the first coordinate to 0 and the 10th coordinate to 1? What is now the correlation in the coordinate 2 and 5? So this is going to be what's called the faces correlation matrix. So let's make the following definition, this notation. So remember that, so given sigma in xk, remember that xk in the complex corresponds to partial coloring of k elements. So I'm going to denote sigma as a pair IB, where I is going to be a subset of n of size k. The k elements are going to color, and B is going to be some coloring in 0, 1 to the I. Right? So I'm going to remember the k face corresponds to a coloring of k elements. And I can just denote within which elements I'm going to color and then what colors I want to give them. So now we also need to say what is the correlation matrix given that I already color these elements. So look at 2 of the remaining elements and study their correlation matrix. And it's going to be very similar. So the definition is going to be, let's call this maybe the face correlation matrix. So again, let mu be distribution over 0, 1 to the n. Take some k at most n minus 2, and take sigma, which is IB in x case, so a column of k elements. Now, so define, so the correlation matrix, so the sigma, it's called the sigma correlation matrix. So I already colored k elements. So I have n minus k elements remaining, right? Each one of them could be 0 or 1. So this matrix is going to be a 2 n minus k twice times 2 n minus k matrix, right? Again, because I have n minus k elements remaining to color, each one could be 0 or 1. Its rows and its columns are indexed by basically n minus I times 0, 1. Right, all the possible colors for the remaining elements. And the correlation matrix, again at IA JB, is going to be exactly the same as before, except that now we're also conditioning mu to agree with this partial color in sigma. That's going to be the probability that Zj is B, condition on Zi is A, and also Z on the elements I is B. So here I'm just shorthanding saying conditioned on Z taking the value, the color A on the coordinate I, but also coloring all the elements in the set capital I with the colors capital B, minus the probability that Zj is B, conditioned on 0. Okay, so it's exactly the same as before, except that basically now, if you look at it from the complex viewpoint, we're now in the subcomplex, which is the face of sigma. Right? So this is exactly the same as the global correlation matrix for the distribution on the face of sigma. Again, similar to before now, this only makes sense if I is different from J. And similar to before, we can say that if I equals J, we're just going to set this IA, IB to be 0. Okay, so this is similar to how we were studying complexes and we cared about all the links being somehow nice, let's say expanders. So now we can all the links to have this pairwise correlation matrix and study it somehow and argue something about it. Okay. So this, even though it seems like it's a bit technical here, it's exactly the same as the original global correlation matrix, but now when we just look not on the global complex, but on the face. Or in the link, sorry. Okay, and now we're going to come to the final definition of spectral independence. It's going to say the following thing. So let mu be a distribution over 0, 1 to the n. It is, let's call it maybe, I use a little chi here. Xi, this is Xi. Spectral independence. If the following thing holds, for every k at most n minus 2, for every face in xk, if I look at this correlation matrix, C sigma, spectrally is at most chi. Okay, so this sort of is somewhat similar to if you think about how we define local spectral expanders. We said every link, look at the adjacency matrix of the graph, it should be a good expander. So spectrally it behaves in a certain way, and now we're saying something different. We're saying, well, look at the link, take the pairwise correlation of the colors. This matrix should have small spectral norm. Okay, so this definition of it's a definition. It's still not clear what it is good for, but I'll show you what it's good for. But before showing you what it's good for, let's just see one example. So maybe example one, it was maybe the easiest example. Probably do the notes. So that well, if mu is a product distribution, then size sigma is just 0 for all sigma. So it is 0 spectral independent. We say SI for spectral independent. Well, that's a trivial example. Here's a more interesting example. So we say that mu is called negatively correlated if you ask me what the probability is z from mu that zi is 1, condition on zj is 1, it's always going to be smaller than the probability that zi is 1. Yeah, z from mu. So what is negatively correlated distribution? Again, over 0, 1 to the n. If I see a 1 somewhere, it makes another coordinate being 1 be less likely. Before, so for example, mu uniform over k sets. Right? If mu is just uniform over all sets of size k out of n, over the k1s and n minus k0s, then sin 1 makes another place be slightly less likely to be 1. So this is sort of like a much more general notion of sort of being, this is not independent, but somehow being negatively related to each other. Another example that's still true but harder to prove is also mu uniform over spanning trees. Turns out that the uniform spanning tree, when the basic objects are edges, is also negatively correlated. So that's like an interesting fact, but it's sort of harder to prove. And now let me just prove you this claim. Let's say as well, if mu is negatively correlated, then it is 1 spectral independence. Actually, it's not. This is not true. If I just know it's negatively correlated, then we already know something about the global correlation metrics. But actually, if you know that the distribution is negatively correlated, and also if any restriction of it is negatively correlated, which is usually the case in most examples, then it is 1 spectral independence. But I'll just prove this claim. Okay, but what I just said is of an immediate corollary, right? If a distribution is negatively correlated, and this stays the same under every restriction, then it is 1 spectral independence. So let's just prove this claim. So you'll see why spectral norm sort of comes up naturally here.
Shahar, is there an obvious example of something that is globally negatively correlated, but when you move to a link, it's not?
Probably could cook up something, right? But I think that all the natural examples are closed under restrictions. So yeah, but I'm sure you can cook up some artificial example. Actually, let me skip this claim because we have the proof in the notes and we only have 27 minutes left in the end of the quarter. So I want to focus more, how this notion of spectral independence is related to what we've seen to analyzing this sort of global dynamics. And yeah, if you want, you can read the proof in the notes. So the main thing here that helps you is this condition allows you to basically bound the L1 of the rows, because when you look at the difference between the probability of Zi is 1 condition, Vj is 1 versus Zi is 1, it's always have the same sign. So you can actually easily analyze the L1 of the row, and so things cancel out and you get a very nice bound. So, but I'm going to skip the proof here. So it's 5 minutes, but no, we don't have these 5 minutes. So I'll skip it and you can read on your own. The main thing I want to show you is the following theory. So this is really the reason why we defined it. This is the theorem of, it said that, so remember, so recall, let's do it this way. So let mu be distribution over 0, 1 to the n, which is spectrally independent. Let x pi be the corresponding complex, weighted complex. Then for every k at most n minus 2 and every sigma in xk, we get the following bound, lambda 2 of x sigma. So this is sort of the standard bound on lambda 2 of the normalized adjacency matrix for this link, which is what we analyzed so far, is smaller than this bound c over n minus k minus 1. By the way, in the notes up to an hour ago, there was a typo. So if you print that an hour ago, it said j, but there's no j in this statement, just k. So what is interesting here? So think about c being, let's say, 1. Like the case we have for negatively correlated distributions. So if you think about the bottom link, the link corresponding to sigma being the empty set, k0, you get a really good bound about c over n, c over n minus 1. So you get a really good bound on the bottom links, and this bound deteriorates as you go up the complex. So actually what we get is the opposite behavior as the one we've seen in the trickling-down theorem. In the trickling-down theorem, we said we prove some bound on the top level And assuming the complex is connected, this bound becomes worse and worse as you go down in the complex. Hopefully it doesn't become too bad. So we can apply some results. And here we get the opposite behavior. If we prove the complex is spectrally independent, then the top level is bad, maybe C, but the bottom levels are really, really good. And this actually plays really nicely with, what we've seen last time, a level-hour result. So let me just show you one corollary of it. We just basically want the plug and play of this with a level-hour. So assume two things. Assume one, that mu is under the same conditions. I won't keep C spectral independent, which is going to actually, let's assume one here. It's going to be one spectral independence, which is going to give us really good bounds on all the levels except for the top level, right? If I plug in k equal n minus 1, I get the bound 1, which doesn't help us at all. But from level n minus 2 and downwards, it's going to give us good bounds. So also I'm going to assume that just the top level has some gap. And two, I'm going to assume that for every sigma in x n minus 2, lambda 2 of x sigma is more some lambda. Okay, so I'm saying assume some bound for the top level, but then also assume this global structure of one spectral independence. Then we mix the second eigenvalue of the lower walk, un minus 1 dn, is at most 1 minus 1 over . So basically we get something that's significantly below 1. As long as we can prove two things. The global complex is one spectrally independent, and also the top link has some spectral gap. Doesn't have to be really good. To apply Oppenheim theorem, we have needed lambda to be really good, like at most 1 over n, so that you can trickle it down. And now that it could be lambda could be half. That's good enough for us, as long as the global complex is one spectrally independent. So let's prove it and see why. So we call this definition we saw last time of, I think we called it gamma j. So gamma j was just a maximal lambda 2 of x sigma, sigma in the jth level. So ALO results tells us that gamma j is at most, well, c, which is 1 over n minus j minus 1. This is just plug in this theorem of ALO with setting k to be j and setting c to be 1. So just direct application of it. So we get a bound on all the levels. So this is useful for j from 0 up to n minus 2, but it is useless for j equals n minus 1, because for level n minus 1, we're going to get a bound of 1. And 1 could be not mixing at all, not even connected. But then we also know, by assumption, the top level has some mixing. So gamma n minus 2. So this should have been n minus 3 and n minus 2. Here, sorry. Gamma n minus 2 is at most some lambda, which is less than 1. So now we can just plug in a level-hour. So remember what a level-hour told us. It told us, well, what should be the second eigenvalue of the lower walk? It's most 1 minus 1 over n. The product of j going from 0 to n minus 2, 1 minus gamma j. But this is in general true. So now we just have to plug in the parameters we get. So it's 1 minus, or maybe at most. So the last one is 1 minus lambda. Let's move it here, 1 minus lambda over n. And the rest going from 0 to n minus 3, 1 minus 1 over n minus j minus 1. And again, like before, we saw in this case, we get this sort of telescopic sum. It's equal to the 1 minus 1 minus lambda over n is product of j from 0 to n minus 3, n minus j, yes, minus 2 over n minus j minus 1. And if you work out, everything here cancels, and you get exactly what we claimed. 1 minus lambda over n minus 1. So the interesting phenomena here is the following. By getting this global spectral independent structure with a bound 1, it's enough to get some independent control over just a top level, level n minus 2. And then everything else below it you get for free from the spectral independence. If the spectral independence, and goes back to the statement of this claim. If the spectral independence wasn't 1 but was 2, let's say, then we would just need to get some type of control over the top 2 levels, and then the rest would be free, and so on. So in general, spectral independence, in the way we define it, allows us to get meaningful bounds for all the levels except for the few top levels. And if we can get some bounds for the top few levels from some other reason, other understanding of the complex, or maybe we could just use the trickling down theorem for the first few levels in the top, then we can combine everything together using a level up. Because this is the main reason why this notion of spectral independence became so useful. It allows us to get really strong bounds on all the levels up to the very top few, and those we can usually handle independently. And also the bounds are such that if you plug them into a level out, everything cancels out. So you get really nice strong bounds. So the only thing left for us to do, and we'll only skim through the proof, is proving this ALO theorem. Any questions before I do that? Okay. So now, the last piece of it. Yeah, sorry.
You mentioned that the difficulties that arise when you get to the top level, can be dealt with independently. Would you what do you mean by that?
I mean that you're trying to analyze the global dynamics of the lower Wilkinson complex. Well, you know this complex, maybe this complex is about 3 colorings of a graph or something, right? Now, what did we do before spectral independence? We said, well, we're going to first of all, we want to bound this gamma j for all the levels. So we said, well, let's get a really good bound at the top level, and then use the trickling down theorem to get some bound on all the bottom levels. And this bottom bound is going to get worse and worse, but hopefully it's not too bad. So we can put it all together. And now we're saying, well, if you can prove that this global complex is spectrally independent with a good Xi, this automatically gives you good bounds on all the levels except for the top Xi. So if Xi is 1, only one level you have no control over. So before you had to prove a really good bound on the top level. Now you just need a not horrible bound on the top level. You just want to prove that the top level lambda is not super close to 1. Well, before you had to prove it's really close to 0. It just gives you much more freedom in what you can do there.
That makes sense. Yes, I understand.
Like imagine you're studying spanning trees, so suddenly you say, well, what if at the top level I have a spanning tree like single edge? Well, how many spanning trees of single edge can you have, right? You basically going to restrict. So you have very, very simple combinatorial questions to study there. Okay, so usually the things are much more manageable.
I see. That makes sense.
So you're looking at a link of an n-2 phase or an n-3 phase. So it says dimension 2, dimension 3. It's a very simple complex. So usually you can just analyze the things on your own, right? Not by hand. Yeah, good question. Now I just want to mention that since this result came up, people have found other ways of analyzing this spectral independence using other techniques, like something called log Sobolev inequality that we briefly discussed at the end of the notes. But in general, I think people are still trying to find what is a good condition to make the work mix, and people just and this notion of looking at the pairwise correlation just turned to be very, very natural from the viewpoint of sampling. It's maybe less natural when you think about these complexes, but it is more natural when you think about it as sampling. And this was just something people could analyze of, ALO analyzes by hand for some examples, and then other people analyze for other examples, other dynamics and so on. Just something sort of, I guess, turned to be natural to analyze and useful. Okay. So I want to at least skim the proof of the theorem. So I want to prove ALO theorem. So first I want to just mention that actually it suffices to prove just for the bottom length. So if I take lambda 2 of just x, should just mean the bottom level, I want to claim that this is going to be at most c over n minus 1. So if the global correlation matrix is c, has spectral norm c, it's enough to prove that the normalized adjacency matrix of the bottom face of the complex has second eigenvalue at most c over n minus 1. Why is it the case? Well, just because our condition of spectral independence is hereditary, right? If the whole complex is c spectrally independent, then every link by definition is also c spectrally independent, because this is just the way we define it. We define it to be hereditary. So actually here is actually this will actually be enough to just prove something even weaker. We just prove this. So we're going to prove this. That if the global correlation matrix of the whole complex has spectral norm something, then the second eigenvalue of the normalized adjacency matrix of the graph underlying the whole complex is at most this value divided by n minus 1. So the deeper the complex is, the better boundary with lambda 2. So this is what we're going to prove. So how are we going to prove that? Well, we need to somehow connect this global dynamics viewpoint to complexes viewpoint. And to do that, it will actually be useful to define an auxiliary matrix. So we're going to define an auxiliary matrix. I'm going to call phi. But also phi, again, same size IA JB. So again, it's a 2n by 2n matrix. It's just going to be the following. It's going to be, again, the probability that Zj is B condition on Zi is A, but now without minus the probability J is B. If I is different from J, and it's going to be 0 if I equals J. So that's going to be basically, half of the definition we had for spectral independence. But just to remind you, so our definition for psi, so psi IAJB was the same, but we also had minus probability of Zj is B when I is different from J, right? So they had these two components. The probability of Zj is B condition on Zi is A minus the probability Zj is B. And here I'll always be assumed that Z is coming from U, so I won't keep writing it down. So now phi just has one piece of the puzzle. And I want to argue the following thing. So the proof is going to have two steps. So step one, we're going to prove that this A, which is the normalized adjacency matrix for the complex, is just exactly the same as 1 over n minus 1 phi. So we're going to prove that this sort of phi matrix is exactly the normalized adjacency matrix up to scaling, exactly the scaling I'm trying to get, 1 over n minus 1. So in particular, lambda 2 of A is going to be equal to 1 over n minus 1 lambda 2 of phi, because they're the same matrix up to scaling. And then step 2, we're just going to compare phi and psi, and we're going to prove that lambda 2 of phi is smaller than the norm of psi, so the maximum eigenvalue of psi. In fact, it's going to be the same, except for some very trivial cases. So in most interesting cases, it's actually going to be the same. So I'll say so in most cases, that's actually going to be inequality, not just small. So that's a high-level structure of the proof. So let me just show you quickly do step one. So let's analyze the quantities that we care about. So let's look on the probability that Zi, sorry, let's see. What is the probability that Z of I is A? Well, let's define U to be this element IA and V to be the element JB that's going to come up soon. But both U and V are nodes of the complex at level 1. So what is the probability that Z of I is A? Is exactly summing up all the probabilities, right? This is exactly going to be the sum over mu over all sigma, where sigma of I is A, right? Where sigma, and what is this? I'm claiming this is exactly going to be pi n of x u. So remember, the top level pi n is exactly mu. So summing up all the probabilities of the colorings where I color the element I by A is exactly the same as summing up all the probabilities of elements which contain U as one of its elements. Remember, the top level faces are full colorings. U says color element I by color A. XU is the link of U. It's all the full colorings consistent with U. So pi n of XU is sum up all of these colorings that are consistent with U, which is the same as sum up all the coloring, color element I by A. And what is this? I'm claiming this is the same as n times pi 1 of U. Because of this connection between pi n of a link and pi, in this case, 1 of the, the face defining the link. So by a very similar reason, what is the probability that Zi is A and Zj is B? Well, it's again summing over all full colorings consistent with I and J. So for the same reason, it's going to be pi n of the link of U and V, right? All the full colorings consistent both with U and with V. And again, here I'm assuming I is different from J. And again, for the same reason, this is going to be n choose 2, pi 2 of UV. So what is, so what we cared about is this probability that Zj is B conditioned with Zi is A. So this is going to be the probability that Zi is A and Vj is B divided by the probability that Zi is A. So just plugging in these things. Sorry. What happened here? Sorry. My iPad is doing something weird. Okay. So what is this? Just plug in, it's going to be n choose 2 pi 2 UV over n pi 1 U, right? Which is just going to be n minus 1 over 2 times pi 2 UV over pi 1 U, right? So this is our matrix. This is what we care about. This is going to be the matrix phi at IA JB. Now let's compare this to A. So what is A? A, the normalized adjacent symmetric. What is A of IA JB? So it's going to be pi 2 of UV, right? The weight of this edge divided by pi 2 of the link of U, right? This is just how we define the normal adjacent symmetrics of this walk. So it's a weight of the edge normalized by the sum of the weights of all the edges touching u. And this is going to be phi 2 uv over twice phi 1 u. So it's very, very similar, except that the normalization is different. So this is exactly going to be what? 1 over n minus 1, this phi. So we get exactly the bound of 1 over n minus 1. Because of this transition from looking at the correlation matrix globally to looking at the link locally on the nodes. Now this only analyzes the case of I different from j, and also you can, it's easy. So if I equals j, then by our definitions, A, IA, JB is the same as phi, IA, JB is 0. So they're both 0. Well, for phi we defined explicitly, and for A, if I equals j, then IA and IB never appear in a phase together. So anyway, you can just check it on your own later. That's sort of in the diagonal cases, y and j are the same, both are 0. And in the interest in off-diagonal cases, they're exactly a factor of 1 over n minus 1. So I know this was a bit fast, but it was in the notes. So this finished proving part 1. But basically, analyzing the normalized derivatives is exactly the same as analyzing phi up to the scaling of 1 over n minus 1. So now all that I have to do to finish is basically prove sort of step 2. And I have like 3 minutes, so I might go a few minutes over time. So okay, so let's do that. So the idea is basically to look on the eigenvalues. So step 2. So we're going to compare the eigenvalues of phi and psi. So first, let's look on the all one eigenvalue. So let's say A. Let's look on the all one vector. So what is psi 1? So let's just write it. Let's look on the. I guess I should do it by the IA coordinate. That's going to be the sum over all j not equal to I, and the sum of all b in 0, 1, just because I multiply by 1 of this matrix, which is going to be the probability Vj is b condition on Zi is A minus the probability that Zj is b. Right? This is how we define psi. And it's defined this way: if I is different from j, if I equals j is 0, which is why I'm only summing over j different from I. Now, what's the whole point here? The whole point is I'm summing over b being either 0 or 1. So what is this? What is the sum over the probability of Zj being b? If b is 0, 1, I cover all options. So this sum is going to be 1 for every j. But what about the probability that Vj is b condition on Zi is A? So fix Zi to be A, subdistribution. Well, Zj is either 0 or 1. So if I sum both options, I still get 1. So this is true for every j. You get the sum of 1 minus 1, 0. You sum 0, you get 0. So the all one vector is an eigenvalue of psi with eigenvalue 0. And similarly, you can show that if you do it for phi, by a very similar calculation, well, it's going to be the same thing. But not just of the first term. Right, no second term. Again, this sums to 1, but it doesn't get cancelled by anything. So I just the sum of all j different from I, so I get n minus 1. Okay, so the all one vector is the common eigenvalue of psi and phi, of psi with eigenvalue 0, and with phi it's eigenvalue n minus 1. Okay, this was part 1. part 2 is the following thing, so B. So we're going to define the following vector. So EJ is going to be the following vector. It's going to be, so EJ at coordinate IA is going to be 1 or 0, 1 if I equals J, and 0 if I is different from J. So remember, I have 2 n coordinates. So EJ is going to be a vector with 2 1s and the rest 0. It's going to be 1 in coordinate J0 and J1. And it's going to be 0 everywhere else. So it's going to look like 0, 0, 0, 1, 1, 0, 0, 0. So these are coordinates, J0 and J1. So this is EJ. And let me define U to be the span of E1 up to En, but orthogonal to 1. Okay. And I'm claiming, and I won't do the calculation here, but by doing a similar calculation to the one that is above, just because multiplying by EJ sums both options for BB in 0 and BB in 1, you can prove that for any F in U, psi F is 0, and sorry, I think it was going to be so again, I won't do the calculation here, but I'll just tell you what the result is. So yeah, so you get that. So here's what you get at the end. By doing the similar calculation, you get that psi F is 0 and phi F is minus F. Okay. So again, I want the calculation is sort of completely detailed in the notes, but you basically follow the same idea that you sum over ZJ to BB, B0 or 1, you sum to something nice. So it's going to sum to 1. I just need to work out the details. So what do you get here? You get that U is an eigenspace of psi and phi, and psi has, eigenvalue 0, and this one has eigenvalue -1. And then the last piece is looking on the remainder. It's called W to be, U perp. So not U perp, but perp to 1 and U. So it's going to be the span of E1 up to En perp. That's the remaining space. So remember, overall we decompose into 1 orthogonal U, orthogonal W. So U is a span of these vectors E1 up to En orthogonal to 1, and W is everything orthogonal to the rest. And here what you can prove is that for now here you can prove that for any F in W, psi F equals phi F. So this minus part, or the part here with the different, where it's minus probability J is B, is always annihilated if you're orthogonal to all these vectors. So again, it's a simple calculation. You can sort of check on your own later in the notes. So these parts are the same. So they have the same eigenvalues. So overall, what do we get? Overall, well, let's see what are the dimensions. So we have 3 spaces. We have 1, well, the span of 1. We have U, which was the span of E1 up to En, orthogonal to 1, and we have W, which was everything orthogonal to E1 up to En, orthogonal. So what is the dimension? So the dimensions are 1, n minus 1, and n, which sort of makes sense because we are 2n by 2n matrix, so the dimension should be 2n. We just broke it with 3 things. So what are going to be the eigenvalues? And both of them, all 3 of them, are common eigenspaces for psi and phi. So what are going to be the eigenvalues? Well, this last one we don't know. It's something. So let's write here phi and psi. So for phi and psi, because they act the same on the space, they're going to be the same thing. This is lambda 1. So let's call it something else, not lambda. Let's call this okay, call it something else here. Mu, just so that it's not. So let's say for psi, for phi, it's going to be some mu1 up to mu n here, some eigenvalues, and the same here, because they act in exactly the same way in the space. So the only difference is going to be the way they act on the previous spaces. On one we saw phi has eigenvalue. I think it was n-1, and this was 0. And n-1, well, we have n-1 copies, and phi is going to be -1. This is going to be 0. So if we think about what is lambda 2 of phi, well, it's going to be the maximum of all the eigenvalues except for the top one. Well, the top one is the first one, n-1. All the rest are between 1 and -1. So it's going to be the maximum of -1, nu1 up to nu(n). What's the norm of psi? Well, it's the maximum of all of its eigenvalues, but now it's going to be maximum of 0. v1 up to vn. So clearly, we get this inequality, but really they're going to be the same, because the only case where they're not going to be the same is if all the vi's are negative, which is I don't think it can even happen, but maybe potentially it can happen. But in a typical case, some are positive, some are negative, in which case they're the same. So really what we did here, and again you can see the details in the notes, is just a sort of case-by-case analysis of the eigenvalues of psi and phi, decompose them into the common eigenspaces and just comparing the direction of these spaces. And crucially, the space where actually all the action is happening, which is the last one, W, then they act the same. So maybe it's hard to analyze, but they're the same. It doesn't matter. You get whatever bounds for each one. And that's it. So this finishes the proof of this ALO, or at least this is a proof sketch. Hopefully now if you read on your own, it will be easier to understand what's going on. And the only thing I omitted are some calculations that are very, very similar to this calculation I showed you here, just slightly different. And again, the last thing I want to tell you before we finish, and this is going to be sort of the end of the class, is that so also we mentioned at the very end this log Sobolev inequality that we're not really discussing here. And log Sobolev are very, very, they've been around for analyzing Markov chains for a while now. And the main reason they're useful is because if you go back here to this sort of bound, I told you that for general walks on go way up to the beginning of the class here. Yeah, so here in this theorem. So we said in general, if you use spectral expansion to analyze random walks, the bound you pay, assume lambda is a constant, the bound you pay is logarithmic in 1 over the smallest probability. And the main thing here I want to just write is that so again assume here lambda. Let's use the end. Let's go to the end. So you have small space. So now this log Sobolev stuff. So assume lambda is something less than 1, then spectral expansion gives mixing time of something like log pi mean inverse plus log 1 over epsilon, which is what we saw before. And the point is that log Sobolev is a similar parameter. So log of parameter phi less than 1. Again, 1 is going to be trivial. I don't want to define it here, but the main benefit is going to give you something that looks like log pi mean inverse plus log 1 over epsilon. So the main benefit that they give you is that the dependence on the smallest probability becomes from log to log. Why is this interesting? Well, because in many cases, your spaces that you care about are exponential. So pi inverse, even if it was uniform and nice, would be like 1 over exponential. So log of that is going to be linear. But usually linear is something that's lossy. You want logarithmic in n. And log Sobolev inequalities allow you to move from n to log n in this case. But again, this is not really our main thing. And in the notes, we put some references for surveys and books on this type of log Sobolev inequalities. And if you're interested, you sort of can read them on your own. And I guess that's it. So that's the end. So I'm hoping
it's worth noting, maybe Shahar, that people have also recently proved connections between spectral independence and log Sobolev inequalities, which is another reason we're breaking them up.
Oh yes. So like Max said. So people can use now spectral independence sort of directly. Although I'm guessing that maybe at some point you want to replace spectral independence with some other property of the correlation matrices that is more directly connected to log sublevel inequalities. I'm not sure. I don't think what people found out is the end of the road. They just started to figure out things. So things are sort of likely to keep changing. That's my guess. Okay, now the other thing I want to say that sort of, I'm hoping that you got something from this class. It was sort of, a mixture of topics on expanders and high dimensional expanders, and Max and I are going to clean up the notes a bit. Yeah, no, that's it, I guess. Max, you have anything to add?
Nope.
Yeah, so just reminding you, homework 4 is due June 11th, and the project is due, when you can. And yeah, that's it. Enjoy your summer.
Thank you both for running this class. It was really interesting.
Thank you, Professor.
Yes, thank you.
Thanks, Professor.
And I know this online format of suboptimal for these topics, but it was okay.
Okay. I will be back in the fall, though.
Yeah, in the fall we'll go back in person. Yeah.
I saw that you're teaching 200.
Yeah. You want to take it?
I do. I don't know, because I heard it gets like full really quickly.
So it used to get full really quickly, but then usually what we do, we just switch to a larger room. So you don't have to worry about it. So currently, I think the room capacity will be 75, which is more or less what we expect to have. But I'm assuming some students are going to be hybrid. And also, I think some master enrollment have dropped down the last year because of COVID, so we might not be full. And in any case, if we get full, just switch to a larger room, so it shouldn't be an issue. I mean, the only thing you need to do is you need to submit like an easy request.
Yeah. I think that the department doesn't look at them until because I'm an undergrad, right? Like they don't look at them until but I thought that the limiting factor for the class sizes was not the room size, but the teaching staff capacity to
sometimes, but more often than not, it's room size.
I think you can hire another TA if you need them.
Yeah, you can hire an TA if you need to. I mean, you get the number of TAs is linear in the number of students, so that's not an issue. Usually, the hardest constraint is the room size.
Interesting.
Yeah, it's usually annoying. My understanding is for undergraduates. I when I was taking 200, one of my undergraduate friends was trying to get into the class, and she managed to. And the limiting factor then was actually getting Russell to respond to emails. It wasn't.
That's another limiting factor. No, I asked Tierra to first of all automatically approve all the students who have taken 105, and if you haven't, just route it to me. But you've taken 105, right?
Mm-hmm. Yeah, I've taken 105 and 101.
Yeah, I think only 105 is required. But yeah, anyway, I asked her to automatically approve, and she says she's going to do it starting maybe next week or in 2 weeks, like mid-June. She's going to start doing it, so like way before. But what they used to do before is just only do it like a week 2 of the quarter, which I felt was way too late.
Yeah.
So I asked them, no, do it like ahead of time, like the same time as the grad students, and so that people have like enough time to arrange that. Because I think some classes they do have a physical constraint, like if it's a lab, then they have like so many whatever stations or so many whatever, right? Then it's harder. But for like our class, for theory classes, it's not really constrained. So yeah, but I asked Tierra to process all of those, and she promised to do it. But if you just submit the easy request and should either be approved automatically or route it to me, then I'll approve it.
And is 105 adequate preparation, or is the class very difficult if you haven't read the textbook material?
No, it's supposed to. First of all, it's much easier technically than this class. It's much more of like I would say, more of a conceptual class. It's a natural continuation of 105 or 105-like class that we have taken. It's really more about understanding different notions of resources of complexity, like time, space, interaction, randomness, and non-determinism, and so on, and the circuit models, and then seeing how they relate to each other. So the proofs I mean, there's the proofs, of course, but they're much more conceptual,
Mm,
much less technical.
mm,
And also the students who take it come from like different backgrounds. Some of them are theory students, some are like you undergrads who want to take it, some are master students who are not theory students, but they want to understand something about complexity. So it's much more like a mixed class. And yeah, I mean, it's much more conceptual, I would say, than technical.
I see. Okay. And the class, is it like this class, or is it like going to be more exam based?
No, it's more like this class. I don't like doing exams for like no. No, if you want, you can take a look. I taught this class 3 years ago, and it's going to be the same class.
I see. Okay.
Maybe with the same homeworks. I don't know. Because I think I avoided posting the solutions online. In which case, I can reuse it as a homework, or some small variations maybe. But yeah, it's basically going to be the same as the class I taught like 3 years ago.
Teach the class last year?
No, I think last year I taught something else. Was this last year? I forget now.
I TA'd for you.
I took it last year. Yeah.
Pretty
Oh,
sure.
last year. Okay, then you should. Then the one last year was the same as the one 3 years ago, and so I forgot it last year. You sure?
I'm pretty sure I TA'd for it last year.
Oh yeah, you're right. Oh yeah, right. Yes. I forgot. Yeah, it's gonna be just. And did we post solutions?
I was gonna say I was the one who wrote the solutions.
No, I know, but we didn't post.
I think I just posted them on Piazza. I don't think they were posted.
Yeah, that's fine. Oh yeah, you're right. But you used the homeworks we had from like 3 years ago, right? A starting point or not?
I don't remember. I think we used them as a starting point and then modified them or something.
Oh, that makes sense. Okay, so we'll use Max's version of the homeworks. but I think the notes stayed roughly the same, no? Or maybe not. I forget. Maybe some changes in the notes also. Anyways, so either one of the verses, there's going to be maybe another variation of the same class, but yeah, more or less the same.
Okay, that makes sense. I'll take a look at like the and see, like, hopefully I'll be able to get into the class with the easy request.
Yeah, no, it should be. I mean, there are several undergrads who want to take this class, and usually, like, every time I taught it, I put at least like 10 undergrads in the class.
Okay.
It's very common.
Cool.
Yeah.
Is there a prerequisite for that class?
So it's a 105.
It's a theory of computation.
Yes. Have you taken this class?
No, I haven't taken that class.
You may be able to do it. I never took theory of computation. I just wanted to grad complexity. Like it's
yeah. Yeah, I mean, you just need to take this, or have you taken anything related to it? Like, have you done like DFAs, NFAs, Turing machines, stuff like that?
And I've been reading the textbooks by computational complexities.
If you read the textbook, then it's fine. I mean, I trust it. If you know, I mean, if you want to take this class, it's fine by me. You just need to submit this easy request, and then because you don't have the prereq, then it's just gonna be routed to me and I'll approve it. So it's fine.
I see. So I was worried about that. So I was trying to get take that class last year. I was worried about the prerequisite.
But did you try to register and you want them to register, or you didn't register?
I think I can't register.
Well, you can't register automatically, but usually what I ask them to do is just to route all the requests to me, and then I can just review them. And then I just usually ask you, like, no, are you gonna read the textbook beforehand? No, about 105, and say, yes, it's fine. Like, no, I try to trust students, but grad classes,
there's a different form so if you tried to do it on WebReg, you wouldn't have been able to do it. There's a different system for doing this request that you have to go through.
Yes. It's a different form. Yes. Yeah, I don't think you know the WebReg. Yeah, honestly, I don't even know how to submit an easy request, because all I get to see that when I need to review them. But there should be a way to do it. There should be. Max, do you know how to do it?
Google the form.
Yeah, it shouldn't be too hard.
Yeah, I think you should be able to figure it out. I don't quite remember. I've done it for math classes. It shouldn't be that hard.
Yeah, but it's usually better in general to first speak, with the instructor and just make sure they're okay with it, and then it's just an automatic approval.
Yeah.
I see. So that's a class for next quarter.
Yeah, in the fall. Yeah.
I see. That's great. Yeah, thanks for the class. I've been learning a lot of the expanders. Yeah, I think it's also be very useful in the physics, in the quantum information field.
I hope so. Yeah, I think definitely this work about quantum codes. But I think, well, some of them rely on HDX, some of them are more topological. like the first ones. And yeah, I think there's still an interesting question there, like what would be the right approach? Because these topological approaches, for the first construction of of quantum code, of like CSS codes, they were like very weird from like the standard coding perspective. That's not something you see in other places, and it's not clear. I mean, there's this Zemo-Tillich. You know this Zemo-Tillich construction, right?
Yeah.
Yeah. So this one is much more classical, I would say. And now there's newer works, but to me, it still feels like it's still unclear if there's like a better principled way of design, like stabilizer codes. But also now I know, again, I don't know much details, but I know people have come with other notions of codes, like approximate codes that I don't quite know what they mean even. But something that's not stabilizer code, but like a different family of code that maybe is good enough.
Approximate.
Okay, sorry, 1 second. My computer is plugged, but the battery is running out. Yeah, I mean, so I know this notion of stabilizer codes as this classical notion of quantum codes, but there was like a paper in Stock of Fox, like I think last year, where they have like a better construction of some type of quantum code that is not a stabilizer code and only allow you some approximate stabilizer type properties. Again, I don't know the details. I didn't look through it, but I know people now have other notions of quantum codes that might be good enough.
Do you know the authors?
I don't remember, but we'll try and find it. Let's see. I'm just going to go with papers in Stock 2020 and Fox 2020 and see if I can maybe check if it's one of those. Let me just check one thing.
Yeah, actually gave a general talk in the physics department yesterday about the expanders.
Oh,
and the relation to the quantum codes.
1 second. I don't see the Stock 2020.
Are you talking about the approximate quantum LDPC codes?
Yes.
Yeah, I found the paper. Hold on.
Okay, good. So where was it? Not Stock?
Stock 2019.
Oh, 2019, the one year before. Okay.
I mean, I'm sure it's on archive. There's the ACM link.
Yeah.
If this is the one you're talking about.
Yeah, this is the one I was talking about. And again, I don't know. Or I don't know, or maybe definitely the words approximate quantum and LDPC in the title. So it's probably this one.
Pretty good.
Oh, I thought there is a approximate quantum error correction.
Yeah, I don't, but yeah, I didn't read this paper, so I don't know what they mean. I mean, actually, at some point, like a few years ago, I spent some time trying to prove lower bounds for stabilizer codes, or even for like CSS codes, but I couldn't do it. But it leads into like very natural questions like in analytic combinatorics that I like. But yeah, then I wasn't able to prove it.
Were the lower bounds you were trying for not broken by Tally's construction? Were they stronger?
No, that's wrong. So here's like the one. Here's like the first conjecture, so that you don't have let's say a stabilizer, let's say even a CSS code with constant rate and constant distance, and constant sparsity. So I mean, constant like sparsity is actually constant, and a constant relative distance and relative. Yeah. No, so I think what Tally did, they would like improve some polynomial factors. So they proved, so the Zemo-Tillich construction gives you I think linear, well, I forget if it's linear rate and like root and distance or the other way around. I forget exactly which one. One of them is root n, one of them is linear n. I forget which one is which. I think maybe it's like linear rate and root and distance. And what Tally did was given like root and polylog distance, but then much smaller rate, like polylog rate or something like that. So actually, as the code, it was much worse, but they broke this root and barrier. And then there was this other work, I think by Ryan O'Donnell and some people that claimed to get into some other constant, maybe 2/3, but then there was a bug in it. I'm not sure.
But then there was another one that was right, I think.
What's that?
I thought there was then another one that was.
Oh, yeah, maybe. And I'm not. Do you know what they got there?
I don't remember. I just remember that I thought Tally said someone ended up beating their results and it was actually correct, but that she thought that that the topological HDX ones would still end up being better. I don't really know much about the.
Yeah. So my sense is just coming from some connections to locally decodable codes and locally correctable codes. It sort of combinatorily looks similar. So concretely, so here's a conjecture, but I have no clue to prove it. So if you like a CSS code with sparsity, let's say order 1, then and let's say it has rate omega n, then its distance order n to the c or some c. So this is a conjecture. So you can't get to like linear distance. And I mean, I have some intuition why this should be true. Basically, because of similar phenomena happening in like in locally correctable codes, but the combinatorics is sort of different enough that I don't know how to prove it.
So there is no concept of dimension for the code involved.
Well, there are 3 parameters that you want from the LDPC, even a standard LDPC code, classical one. You care about the sparsity of the generated matrix, right? And ideally you want to be as constant. You want the rate of the code to be linear in n, right? Sort of, this is sort of the ratio between the length of the messages and the length of the code words. And you want the minimal distance to be bigger, linear in n. So like in classical LDPC, so for classical LDPC, so you can get sort of sparsity order 1 and a relative rate and distance to be on it. And this actually even holds like a random LDPC, like for sparsity 3. This is even true. This holds for random LDPC, I think even for sparsity 3. Basically because of like random 3 and 5 graphs are good expanding a lot, not have short cycles. But then for quantum LDPC, this is not known. Random doesn't seem to work, and at least not for CSS constructions. And yeah, I don't know. So but then if you take for example for locally correctable codes, which is another notion of locality, classical one, then it's known that if the sparsity is order 1, then it's known that the rate, or let's say, and the one way, if the message length is k, then the code word length so this is known. So the rate is actually bad. If you want good, and anyone good distance, if you have this and constant distance, then the rate is bad. And this is a completely combinatorial, but this actually breaks down for sparsity log n. So if log n is low bound stop working, and the constructions are much worse. So the matching constructions are much worse. They have sparsity basically sub-exponential. So let's see, something like something like that. So something not polynomial, not log, something in between. Maybe c is a half, I think they get. So in general, for the classical case, we don't really know what's happening. It's been studied for like several decades now, since the 90s. We don't know. But at least for sparsity up to log n, we can prove that you cannot have good codes. So I'm conjecturing that for quantum codes, the same phenomena happens, because combinatorially they have similar properties. But up to sparsity log n, you do not have good codes. But I think proving it seems much harder, so I don't know how to do it.
Now a theorem for quantum CSS code, maybe like in 2 dimension. If the sparsity is O1 and there is an upper bound for the codistance, the product of the codistance times the rate is upper bounded by some constant.
Yeah, but you're thinking about some topological, some constraints on the code, right? It's 2-dimensional, right? And I think forget about these physical constraints. You just have like any code, right, coming from any type of stabilizer system. You forget about how hard it is to implement it in practice. No. So basically, what you have is you can model this as basically having 2 classical LDPC codes that are orthogonal to each other, and asking about one conquered by the other. So I'm claiming or conjecturing that there is this lower bound, even ignoring all these sort of physical properties. Can you embed this in 2 dimensions and so on? Which of course you do care about in constructions, but ideally you want to prove lower bounds even if you don't have this constraint.
Is there any review paper on this subject?
Well, again, it's not really my main area. So I'm not really following this area. I just have thought about it at some point because of its connections to additive combinatorics, these combinatorial questions, which is more of the stuff I'm working with. Yeah, but construction, I'm not sure. I mean, I don't really follow them.
Let's see.
Yeah, I don't know that some of them came from HDX and some of them came from other approaches. Right. Yeah, but we need to go, Max. We have a meeting now, right? No?
Yeah, I've been sending emails saying that we're delayed.
Oh, I see. Okay. Good. Okay.
Thanks for the class.
Yeah. See you. Bye.